Hello there, you're on Vectorly, and today we are going to solve the next four problems from rotational mechanics. Rotational mechanics seem to be hard until you know the logics behind it. There are few important methods and steps which are commonly used in solving all these rotational mechanics problems, which mainly include conservation of angular momentum, conservation of energy, and force equilibrium, torque equilibrium. All those kinds of problems coming in rotation mechanics include at least two of these procedures. So let's go through the questions. Question number one. A cylinder of mass 2 kg is placed on a two parallel rails inclined at an angle of 37 degree to the horizontal. A load of unknown mass is suspended from the light inextensible cord wound on the cylinder. The cylinder is held initially at rest and then released. If the cylinder starts rolling up the rail without slipping, what should mass of the load be? So if you see here, this is a cylinder. Due to the force mg sin theta downwards along the incline, it will try to go down. Okay, but we are putting a load attached to it in this direction. Okay, so this tension will give a torque in this direction. Okay, so this will try to prevent it from going down at some particular weight. Okay, let's assume that weight to be m. At that particular weight, this whole system is in equilibrium. If we increase this particular m, this whole thing will move up. If we decrease this thing m, this system will move down and m will go up. This is the main logic behind it. Okay, now if you see the free body diagram, this is a particular free body diagram of the cylinder, which is mg sin theta along the incline and mg acting downwards. Frictional force is acting in this direction and tension is here, and the component of tension along the incline is t sin theta. Okay, the reference is mg is also downward, t is also downward. Mg component in this direction is mg sin theta, so t component in this direction is also t sin theta. Okay, you may ask the question, why a frictional force is here? First of all, but if you see, if friction is not there, what would happen is they didn't mention any frictionless thing, but in that case we have to assume a friction. Why? Because they have mentioned that the cylinder is held initially at rest and then released. The cylinder starts rolling up, so they are saying that the cylinder is going up, so there must be some force which pushes the cylinder upwards. If you see in this free body diagram, the tension component is in this direction. If friction is not there, every force, each and every force is pushing in this direction. So we won't get any force, any real force to push it upwards. So friction is necessary for this particular condition. Okay. Okay, let's first calculate at which m this whole system is in equilibrium. For that, as said, we are going to conserve force. So this tension is nothing but mg because this block is at rest with respect to ground. So T is mg. And over here, along the inclined plane, I'm just conserving the forces, equilibrium. So F friction force is nothing but T sin theta plus mg sin theta. So F is T sin theta plus mg sin theta. Now let's go for the torque. Torque about this particular center. For doing torque calculation, the center should be selected where maximum amount of forces intersect. Here T mg is there, so this is the maximum point. Okay, this seems easy to, because all other distances can be measured from here. Each and every distance is the radius. So T minus F. Anyway, if this is going upwards, the torque should be something like this. Angular acceleration should be like this. So T should be dominating. So T minus F into R, which is 0. I am considering the limiting condition, which is equilibrium. So T is nothing but F. So if T is F, I will replace F with T and replace T with mg. That's it. That m is the necessary part. So if I calculate in that way, I get m is m sin theta by 1 minus sin theta. If you see, sin theta is given already, m is also given. So on net result, this is the equilibrium value. But we found out at the equilibrium, what should be the mass of the load to move it upwards. So m should be greater than this particular value which we found out. Okay. This is the solution for the first question, which is very much easy question. I just gave it as an introduction to rotational mechanics, how we approach these questions. These questions, first thing I did was force equilibrium and torque equilibrium. That's it. Question number 2. A light rigid tube is welded along a diameter of a uniform cylindrical pipe of mass m and radius r. A bead of mass m connected by two identical light springs, each of force constant k, can slide inside the tube. Other ends of the spring are connected to the pipe as shown in the figure. The pipe is held motionless on a horizontal floor. The bead is pulled aside a distance x away from the center of the pipe, and then the pipe and the bead both are released simultaneously. If the cylinder rolls without slipping on the ground, find the acceleration of its center immediately after the system is released. So what happens is, initially these two are identical springs, okay? Each of length, it must be r, because in order to maintain an equilibrium state it should be equal. So this particular block initially would be at the center, and each length of the spring in relaxed state is r. Now what are we doing is just compressing it and keeping in this position. In this particular position, if we just release it, what happens? Let's analyze the situation. This particular block, due to this spring, it will try to move in this direction. What is the force at this particular extent due to this spring in this direction is kx. Similarly, this will try to pull it right with the same magnitude kx, because the extension is x in both cases. So 2kx is acting in this particular block and mg is acting downwards. That's it. This is a free body diagram of this thing. Okay, and what are they saying is, if the cylinder rolls, if we just release it, how will it roll? So there must be some force acting over here. Okay, that's friction in this case, which will make this whole system roll. Else if friction is not there, there will be only linear motion. No torque is acting in this system. So friction is there with normal reaction n. And let's see, if this is pushing this with kx force, the same force will be acting in this direction too on this particular tube. Similarly here it will pull this with kx. So I have written kx, which is pulling, and kx over here. So on a whole, this whole system is given 2kx force in this direction, and this particular block, not whole system, this tube is given 2kx force, and this block is given 2kx force in this direction. So let's assume this tube is moving with an acceleration a, linear acceleration a, okay, which is pure rolling, because they have mentioned without slipping. And what about this? This guy is moving in this direction with some acceleration a1, let's suppose. But what are they asking? Find the acceleration of its center. So they are asking this center lies in this. Okay. If they ask the center of mass, we have to find out this a1 too. But they are just asking its center, so we have to find the a. That's it. If you see properly, we know the accelerations. So let's write the force equation from the ground frame. If you write the force equation, 2kx is the only horizontal force minus f, friction is there. So 2kx minus f is nothing but ma, because we are moving in this cylinder. We did not consider this. We want only a. Similarly, if we conserve torque, what happens is, this mg is also giving a torque in this whole system. The torque we are calculating for the system. So this friction into r and mg into x is nothing but I alpha. So what is I? So I is nothing but the combination. We are considering the system, right? So I is nothing but this plus this. So for this m into x square, and for this mr square. So if we do it, and as it is a pure rolling, alpha is nothing but a by r. So if we write, I am replacing f with 2kx minus ma everywhere. So and if I put over here, I get the final thing in which a is eliminated. So I get a is nothing but 2kx into r square plus mg xr by 2m r square plus mx square. The only thing you want is, if you have what things that I have assumed, a and f. So I need two equations to find these values. Okay, so I have these two equations, force equation and torque equation, to eliminate these two, acceleration and friction, so that I can find any of both of these. Okay, I found the relation between f and the a. So I will replace the places where f is there with a, so that I can find a. So if we have n number of variables, you need n equations to solve it. Question number 3. A rigid lamina is sliding on a horizontal floor with one of its flat faces on the floor. The floor is represented by the xy plane, okay, of a coordinate system. At an instant, some of the velocities of components of three particles ABC of the lamina when they occupy positions origin 1, 2 and 2, 1, or they have given some values. Find coordinates of the instantaneous center of rotation at this instant. This is a much easy concept. They would use, they are asking it in JEE mains too. But the main thing we have to know in this thing is, if any particular system is there of any rigid body of something, if at, let me draw it, at one portion it is moving in this velocity and other it is moving in this velocity. If I draw the perpendiculars of this particular thing, if they match over here, this is the instantaneous center of rotation. Okay, this must be the instantaneous center of rotation. Okay, this is what the concept of instantaneous center of rotation. But how will we find out in this case? Okay, they have given the some components, sorry, VBX and VYC and VAX and all these things. We have to find the center. So let's assume the center to be RC, okay, which is xi cap plus yj cap. And the main thing you have to know is this particular formula. So which is V bar is nothing but omega bar cross R bar. So this R bar is from center, from point P, from center C. So which is RP, that is a point minus R vector at the C. Okay, this is the only equation which you have to know. This is a basic equation. Okay, now I'm just substituting all my points over here. So if as this lamina is in xy plane, it's moving in only in xy direction. So its omega should be in k cap or minus k cap. So this the omega can be negative as well as positive. We don't know the value, so I am just assuming it as omega. Now I am substituting this. We have 3 points, so I'm just substituting it over here. So if I substitute over here for A, I get this particular equation. Here involves the cross product. After cross product, I get this equation for B and C over here. So what are they asking is, they are asking me X and Y. So I have three variables, X, Y and omega. Okay, but I have three equations for A, B and C as well. So I'm just equating it. 2 is nothing but omega into Y. I will write it in here over here. 2 is equal to omega Y, equation number 1. What is equation number 2? 4 is equal to omega Y minus 2 omega. So this is equation 2. What about the equation 3? The equation 3 is 2 is nothing but 2 omega minus omega x. So this is 3 over here. So if I substitute it over here, this is omega y equal to 2. What I get is omega is minus 2. This doesn't need much calculations. Okay, omega is minus 2. Sorry, minus 1. Sorry, this minus 1. So 2 minus of minus 2. So which is 2 plus 2, 4. So omega is, if omega is minus 1, y is supposed to be minus 2. Correct? I found. So we found y. The next step is we have to find x. Substitute this in equation 1. So 2 is nothing but minus 2 plus 2x. Okay. So x is 2. So simple. We got x and y. So what are the coordinates of the center? It's nothing but 2 comma minus 2. So 1, 2 and minus 2. So this is this coordinate of instantaneous center of rotation. So which can be termed as center. So the simple procedure is V bar, V vector is nothing but omega cross R. Okay. There are many shortcuts to remember these formulas too. If you want them, just comment. Question number 4. A load is suspended from one end of a uniform rod of mass 10 kg and length L with help of a light inextensible thin cord, and the arrangement is placed on a fixed horizontal frictionless cylinder of radius R. as shown in the figure. In equilibrium, the rod stays at an angle theta, which is 30 degree with the horizontal, and distance between the point of contact of the rod with the cylinder and top end of the rod is eta, which is 1 by root 2 times the radius of the cylinder. Find the mass of the load and ratio of length of the rod to the radius of the cylinder. So, on conclusion of this whole paragraph, it says some simple constant. This whole system is in equilibrium. That's it, the first condition. So, we can equate torque as well as force over. This thing is concluded. As there is no motion, we don't consider energy or angular momentum over here. Simple. Just two equations. So we need to assume at least two, that's it, two maximum, at max two variables. Okay, I'm just assuming this angle to be alpha. Okay, this is not an actually this is not a variable. We can find this value alpha. Why? First thing, on your in your circles chapter, you know this thing. These two are tangents from the same point, same external point. So these two lengths are equal. So it is eta r and this is also eta r. And the radius is always perpendicular to this tangent. So we get angle alpha over here. So this is r and this is eta r. So I just draw a triangle over here. Okay, that's it. Now I'm just doing this thing. This angle is 2 alpha. So I'm writing 2 alpha. And the component of this perpendicular to the rod is perpendicular is, I'm assuming, t dash. So t dash is nothing but t into sine 2 alpha. So that I have written here. And this thing is also in equilibrium, right? So t is nothing but mg. So I have written here. Okay. So what we have to find is we need r by l and m. Okay, first I'm writing the torque balance as they have given a uniform raw of mass 10 kg for approximate average answers. Exactly for this question, they need approximate and average answer. Okay, so they will consider mg at the center. Okay, not over here. This is the center axis. They are conserving at this position because normal reaction n will be acting here. Okay, normal reaction n will be acting over here, not in this direction. So it will be acting in this direction. Okay, so and mg will be acting downwards. So with respect to this point, we are doing torque balance. So mg they will consider acting at the center of mass of this rod, and this tension force creates some torque, right? They will consider t dash into L by 2 minus eta r. That is the average thing. So they were there is that method is used for averaging, but we need the exact value, right? So I'm just integrating it as they are mentioned it as an uniform rod. So as it is an uniform rod, I'm just assuming the linear density sigma to be m by l. Linear density is supposed to be lambda. I'm just assuming it as sigma. Okay, so I'm just integrating the torque produced by on the one side, sorry, this side, and t dash equal to this side. I'm just writing this, and this is the final equation after integration. And if you do the average thing, it these steps can be reduced, but you won't get the exact answer which is required for this question. So I'm just skipping the second part of the question in which we have to find the ratio of length of the rod to the radius of cylinder, because that requires this thing on solving this. This is the exact method. If you want to take the average thing, if this, just try this method. If you have attempting in an advanced question, just use this method. If you see this method doesn't give the required solution, just shift yourself to the average method. Okay, now let's go for the force balance. So for force balance, let's balance along the rod. Okay, so mg into sine theta, mg sine theta will be acting in this direction. Okay, mg cos theta will be perpendicular, mg sine theta will be acting in this direction. Okay, mg sine theta will be acting in this direction, and t cos 2 alpha will be acting in this direction. Okay, so on overall these two get equated. So mg sine theta is nothing but t cos 2 alpha, so that the rod won't move in this direction. It won't move in this direction. It is not also moving in this direction, but we don't know the normal reaction over here. So we are not using that part of the equation. So mg sin theta is nothing but t cos 2 alpha. So what am I doing is, now mg sin theta is T is nothing but mg, which is the required mass into gravity. So if I divide it, mg sin theta by cos square alpha minus sin square alpha is mg. And if I cancel g, I get m is m sin theta by cos square alpha minus sin square alpha. And from here I can write cos alpha as eta r by under root r square plus eta square r square. That's it. Everything gets simplified. So I get m in terms of m sin theta and eta. Okay. If from this thing I found out one value, so this particular part is completed. For the second part, I need this part of the equation, which you can proceed it with average method, but I have done the exact method. In this exact method, you may or may not get the answer which they are asking. Okay, so just give it a try and do comment all your doubts regarding rotation mechanics, and we will be uploading the problem PDF for rotational mechanics soon. Thank you for watching this video. Kindly do support the channel. Stay tuned.